So we've introduced the idea of statistical power. It's kind of an add-on or complement to this idea of hypothesis testing. Hypothesis testing is kind of just like the first step we might do to evaluate if a sample is different from some population mean, sample mean, or two samples might be different from each other. So we'll just say x bar equal to mu. This is our null hypothesis, and then our alternative hypothesis is that they're not equal, right? And we can do a t-test or a z-test to determine that. And when we do a t-test, you know, we're doing, for example, we'll just say z-test. Z is equal to x bar minus mu all over s square root of n. When we calculate that z-score or statistic, what is that number? And how do we use it to perform a hypothesis test? Yeah, we use it to reject the null hypothesis. And how do we reject the null hypothesis? Yeah, so we calculate some critical z-score value. If I can get this thing to work for more than 30 seconds. So this is my distribution of my, actually, sorry, this is my distribution. Distribution of z values, and a z of 0 means that the mean from my sample is the same as the population mean. We calculate, if we're going to do a two-tailed test, which just means they're not equal, then we calculate these z alpha over 2 values, z1 minus alpha over 2. So that's our critical threshold, right? The critical score that we have to surpass either positive or negatively. We calculate our z-score right here, whatever that is, and if it's on this side, if this is z for x bar, if it's on this side, then we can reject h naught, and if it's on this side, then we don't reject h naught. All right, that's the basic hypothesis test. How big is our z? Or how small is our z? How extreme is our z? And really, all that's comparing is the mean of your sample and standard deviation of your sample and sample size with this expected value of z. So how extreme is this mean value compared to the population? You're really just comparing it to this population, which represents the null hypothesis, that the means are the same. But like I said, that's really only part of it. And if we go over here a little bit farther, and I'm going to just, well, we'll just draw a new one underneath. All right, so we've got our z distribution, our normal distribution. I'm going to draw a little bit farther, give ourselves some more room here. And this, again, represents our null hypothesis. And we could call this really just mu, right? It could be any value. Now we could also draw a distribution representing sample means from our alternative hypothesis. Our alternative hypothesis is that they're different. In this case, they're bigger, right? So this would be x bar. I'm kind of messing with units here. this is actually Z down here, but you can find X bar and mu, by inverting that equation, right? So this is, we'll say Z, but we're just kind of representing these values as centered around mu and X bar. Now, if we do our hypothesis test, we calculate these Z critical values. And we see how far our particular sample mean is away from the population mean. Then that's our hypothesis, which we just talked about. Within this area, which is alpha, right? Alpha is, we'll set it, we kind of always talk about 95% confidence intervals. So alpha is 0.05. That's the area on either side of these tails. But we also have some other things. We'll talk about alpha a little bit more in a second. We also have some other things we consider. We can consider some other types of areas. So let's look at, if this is in fact, we'll just assume that our sample is different from the population. So the chocolate chip cookies, which I will bring, I have them, they're downstairs. I'm gonna grab them after our break. We happen to buy, without realizing, extra chocolate chips, and the stated number of chocolate chips and cookies is, the Chips Ahoy cookies is 16, but in fact we found that on average our cookies have 20. All right, so they're different. We're assuming they're different, and in fact, if we did 1,000, if we counted the number of chocolate chips in 1,000 cookies, or in a bag of 1,000 boxes of cookies, right? So each box is a sample. We would get a distribution like this, maybe. So this represents the true distribution from our sample. And as you can see, just kind of given the way I drew this, that we have a high chance of having an X bar value from our sample that is on this side of that critical Z value, right? So this is a pretty big area over here. It's the majority of the area. So this is like a relatively powerful experimental design, given the distribution of our alternative hypothesis. So power is represented as this area, or the probability. Say if I did 1,000, I counted chocolate chips and 1,000 boxes of cookies, what's the probability that I am going to correctly reject the null hypothesis? And so we'll just write that out. Given the experimental design. In this case, we have 20 cookies per box. The variability of chocolate chips per cookie is so much, right? And then the difference in the means is of a certain size, right? If I'm trying to test for the average, stated average is 16, I'm trying to test for a difference of a mean of 17, well, my power is going to be reduced because this curve is going to go a lot closer to that curve, right? So I'm going to cut into my ability, the probability of actually correctly rejecting the null hypothesis. So put a different way, and I'll write it over here. The power of a study or experiment is the probability that it can distinguish an effect of a certain size an effect is really just a difference, right? A difference in means. Distinguishing that from chance. If we go back to this figure here, given this experimental setup, we have pretty strong power. It's maybe 80% or something like that. But we also have this other side over here. And given this figure, if I say this is 80%, this is 20%, and we'll call this area right here as beta. So alpha is here, this is beta. What does beta represent? If power on the other side of this line, this is power is 1 minus beta. If power on this side of the line says the probability that I correctly reject the null hypothesis, then what's the opposite of that? Type 2. So false negative. All right. Back to kind of like medical testing. I took a COVID test, and I do have COVID, but I came back negative. Right. COVID testing with PCR, I think, has very, very teeny tiny type 2 errors with it. Just experimental design, but there's still error. So beta is type 2. We are in fact sampling from a different population. It's not the same as the null hypothesis population. However, we had some probability that our mean from our sample is not that different from this mean, right? So we're on this side of the Z critical line. So you still get a chance that you're going to have a sample that isn't that different, right? Because you're going to have, most of them are going to be over here, but a lot of, they're still going to have some proportion over here, some probability. So type 2 error, false negative. And if we put it in these terms, we can go back to alpha and say, okay, well, when I do my hypothesis test and I find a Z value that is pretty extreme, I still have a 5% probability that my sample actually came from the population that I'm trying to distinguish from, that it's not in fact different. So I have a type 1 error here, meaning I came from the same population. I'm not in fact different. I just happen to have a really extreme sample. And this is a false positive. It said, well, I reject the null hypothesis. They're different, when in fact they're not. So that you still have that 5% chance or whatever of having a false positive in this case. So the hypothesis test really only thinks about this null hypothesis distribution. That's the whole Z-score, T-score thing. Power assumes, and we don't know this distribution. We can't know this distribution. That's why we're doing the experiment. So there's some roundabout methods to estimate power, which we don't have time to get into. But one of them would involve simulation. And we can simulate, if you say, for example, I have n equals 20. From my sample, here's my variance, here's my standard deviation, my mean. You can create a distribution for that, right? A t distribution. So you can sample from that. Go back to Monte Carlo simulations. Take 1,000 samples from that t distribution, which represents your sample. It represents the distribution of your means. And then you can use that to estimate the power. And that's kind of like Monte Carlo simulation. The other way to do it is to just resample your sample. So if you have a big enough sample, you can go back and say, okay, I'm going to randomly sample my sample again, and you can get the same sample because you're going to get some of the same values, right? And that's called bootstrapping. And so some techniques, especially for data that don't follow normal distributions, there's this technique called bootstrapping, and this is just resampling or sampling the sample. And you can use bootstrapping to create an approximate distribution of your alternative hypothesis or your experimental data. All right. So let's just look at one more example of power. And this comes from the book chapter that I've assigned for this last homework assignment. So let's think about a coin toss. And the question is a particular coin fair? All right, so we'll go toss a coin 100 times. And we'll do that a bunch. And so our random variable is the number of heads out of 100 tosses. And if it's not, if it is a fair coin, then we'd expect to get, on average, 50. We're not, every time we do it, it's not going to be the same, but we'd expect to get 50 on average. We'll have some kind of distribution centered around 50. And this would represent a fair coin. So that would be our null hypothesis, right? But say we did this a bunch of times and we ended up with a distribution that looked like this. And it was centered around 60. So this is our alternative hypothesis. Coin is unfair. And we could do a couple of things here. We could say, well, what's the 95% confidence interval around a fair coin? Well, based on this, it turns out that, just in this example, our confidence interval is plus or minus 10 coins. So if I do 40 right here, then the area under the curve between these two values, 40 and 60, is 0.95. So this is our 95% confidence interval. So we're right there. So we could do our z-score, and we could say, well, we can reject it at the alpha is equal to 0.05. And our p-value is 0.05. It just happens to line up perfectly. But obviously, from the power discussion, there's more to the story there. So can we say that the coin is unfair if we get 60 heads? All right, and based on the z-score or the z-test, we get the z associated with 60 is equal to z, we'll say 1 minus alpha over 2. Okay, so we have a 5% chance of seeing such an extreme value. But the way we do this experiment, the fact that we have 100 tosses, the fact that this coin, for some reason, gives us 60 on average heads, all of these things influence that z-score and the p-value. So it really comes down to experimental design. And the p-value only tells us how extreme that observation is. So we want to look at the power, and what is the power is the probability of being able to reject the null hypothesis given this experimental design. So we talked about confidence intervals. For this particular experiment, you can actually calculate power and plot it as a function of the experimental design. So let's look at that. So in this case, we're going to do power over here. And I'm specifically not talking about how we calculate power because I just don't want to take the time to do that, given all the things that we have to do. So power here, and so of course the maximum amount of power we can have is 1, right? 100%. The alternative hypothesis distribution is really far away from the null hypothesis distribution. Okay, so it maxes out at 100. And then on the x-axis, we have the true probability of heads. So of the coin that we are testing to see if it's unfair or not. So this is the true probability of heads should be 50%, but we could have unfair coins. So 0.4, 0.3, 0.2. 6, 0.7, 0.8. All right, and so I'm just going to draw this. So power is going to decrease as the true probability of heads for the coin that we're testing gets closer to the null hypothesis. So the null hypothesis is that it's a fair coin. And so it's a minimum at this, and of course this would be 0 right here. And then the farther away we get from the null hypothesis, so over here we have a really unfair coin, right? It's 80% of the time we're getting heads. Over here we have a really unfair coin, we're only getting heads 20% of the time. And so of course our power increases because the effect size, the true effect size is actually really big. And so say this is for 100 tosses. But say we wanted to increase our power, we could increase the sample size, right? And so this would be n is equal to 1,000 tosses. And what you see then, this is pretty dramatic, but say that 60% is the true probability of getting heads with this particular coin. Here's my power at 100 tosses, if this is the true effect size. And then here's my power at, I didn't draw that really well, but let's try to draw that a little bit better. Here's my power at 1,000 tosses. So if I increase the number of my sample size, then I can increase my power. All right, so we can increase sample size. And in fact, if you want to figure out, okay, here is the expected difference. Here is the variability of my sample. So say you do some kind of pilot study to get some numbers before you do a really big experiment, then you could calculate the sample size based on power calculation that you would need to be able to detect that difference. So it kind of help do experimental design. So more data like increases our precision, right? The other thing we can do is there variability subject to measurement error? Coin toss is really easy to measure that, right? Measuring velocity in a flume. Maybe there is some type of measurement you do with circuits that is subject to error, or no. You guys have pretty good instruments, but nevertheless, what would be an example of a measurement that can be uncertain in your field? Voltage gives you voltage, right? Resistance gives you resistance. Amps gives you amps. Let's say you're trying to do I don't know, power factor, or like how is that stuff just pretty cut and dry? You guys got it all worked out. All right, fair enough. So, in civil engineering, we're measuring kind of, solid objects or fluid objects. We're prone to measurement errors. So we could reduce measurement error which would reduce uncertainty. All right, so the last thing I'll just say, we kind of talked about this earlier, is doing a statistical test isn't the be-all, end-all of collecting data, trying to prove something. And often, if we get a statistically insignificant result, that doesn't mean we didn't find anything conclusive. Research has certain standards and criteria you have to meet to prove certain things, but at the same time, if we are saying, if you do this, then this happens, you can find a causal link, kind of a fundamental link, right? Either from first principles, through the equations that drive the governing principles that drive the phenomenon that we study. And this actually played out with COVID. And this whole argument of how does COVID spread? And originally it was like, well, the WHO argued that, and we knew that it spread through droplets, right? So you sneeze, you cough, you breathe, you talk, you sing, you're releasing tiny water droplets. And from first principles, we know that tiny water droplets fall out. And there's that 6 foot radius, right? Which maybe that was a 95% confidence interval associated with 6 feet around us. Of course, there's a ton of variables that influence that. But that's kind of where that guideline came off. But they ignored this idea of aerosols for a while, simply because it was too complicated, or and aerosols are like smoke particles. They're just super tiny. They don't necessarily land anywhere, right? If I'm sitting here smoking or got my e-cigarette, that stuff is gonna permeate, and maybe if we turn the air off and close the doors, it'll settle over 3 days or something like that, right? But the idea of a 6 foot radius is pretty arbitrary and not related to aerosols. And we also know that COVID spreads by aerosols. So there is actually work out of CU Boulder that, and there's this kind of famous super spreader event at a choral practice in Washington State that folks who are like really far apart, and there's one person that had COVID, infected a bunch of people because they were singing, and the way the wind currents were, they recreated that and found out that it correlated with who got sick. It's basically how aerosols would spread. So that's a first principles thing. WHO was really hesitant to, and CDC, to recommend HEPA filtrations, things that can get aerosol-sized particles out of the air. So HEPA filters, high-efficiency filters, and they can actually remove smoke particles. So these researchers were saying, hey, if we put some air filters in, they're cheap, it can go a long way to reducing COVID spread. But it took a while for WHO and CDC to jump on that bandwagon. Very simple recommendation based on first principles. If we, I think Carrie worked with you guys in one of her environmental class to look at loading of a certain concentration in the air and how you might remove that. So, you can just do those calculations, right? You don't need a statistical analysis to say if I've got this loading at this concentration of COVID or aerosols or whatever, and I'm filtering out these many air changes per hour, you can just do the engineering calculation. So the recommendations were based off of calculations rather than statistical tests. And in the CDC world, they're thinking about vaccines, they're thinking about public health treatments. Do I get an effect size of a certain amount? Is it statistically significant? And in some cases, you don't need that. You can just do the calculations, right, based on theory. So this is kind of one set of things, and this is important for a lot of types of things we might do in life, or how we can understand things. At the same time, there are other ways to test and make predictions, etc. So I just wanted to talk about that. Any thoughts about power? I don't have you guys do any calculations with it, just to reduce the number of things that we do, but I do have you read about it a little bit more. So this stuff that I just talked about is in that book chapter. I'm going to have you read and answer questions on